All right, so in the last video, we took a maximization problem in somewhat standard form that we discussed. We have to have all inequalities of the less than or equal to type. We have to have variables all non-negative. And all the numbers on the right side of our less than or equal to symbols have to be positive. In general, most of the time, all the numbers we're going to see in these inequalities are going to be positive for most practical situations, but not all. Sometimes when there are negative numbers, that can cause some technical difficulty, but we can also discuss later how to get around that. For now, let's consider these very simple examples. So the point was, we just added three new variables, S1, S2, and S3. We add one of them to each of these inequalities to get a new problem, which is basically the same problem. It just has three new variables in it, which are just there to keep track of information for us. Now that we have equations instead of inequalities for our constraints, we can not only interpret what these variables mean, but we can start analyzing the problem in a more mathematical way as opposed to a geometric or visual way. We're still basically using geometry when we solve these problems. We just aren't going to do it with a picture. So let's see why we do this. So let's look at our new problem. Again, let's just suppose that someone wanted to make a decision. We're going to choose x to be 10 and y to be 12. Right? That decision is probably not optimal, but it is a feasible solution because it does actually satisfy the original inequalities. And I can see that from the new problem. If I plug in 10 for x and 12 for y, then in this first equation, what do we get? We get 10 plus 24, so that's 34. So I subtract that from 150, when I get 116. So S1 equals 116. What that's telling us is that if we decide to make 10 units of product X and 12 units of product Y, then we've only used 34 units of resource 1 to do that, which means we have 116 units of resource 1 still available to be used for other things. We can do the same for the other slack variables. In the second equation, I plug in my 10 for x and 12 for y, I get 30 plus 48, that's 78. So taking that away from 200, I get, 122. So if that's our decision, then 122 units of resource 2 have been unused. And to do the same for the last resource. Again, plugging in 10 for x and 12 for y, I'm going to get 50 plus 12, so that's 62. Subtract that from 175, I get what, 113. So 113 of the 175 units of resource 3 will be left unused if we make the decision to make 10 units of product X and 12 units of product Y. And again, because of our objective function, it tells us what our, say if this is our profit, we would plug that into the objective function 10 and 12, and we see we get 232 for our profit. So it's a profitable decision, it's a feasible decision, and it leaves a lot of resources left unused, which means we could probably make more of the products and then have more possible profit. So that's what we have to figure out, and that's why we want to solve such problems. We want to not only find decisions that make sense, but we want to find the best decision. So since there are so many resources left over with this decision, and it is a profitable decision, it's highly likely that there's a more profitable decision. So we just want to find a way to determine what that decision is. So what we're going to do is we translate our problem as it's written into a more mathematically useful form. And we're going to use matrices just for organizational purposes. And it allows us to do some simple arithmetic on all these equations so that we can basically manipulate the problem and try to find a better solution. So here's what we're going to do to translate the problem. We're going to put all these numbers into what's called a Simplex Tableau. Now I've color-coded this just for this instructional purpose. It's not necessary to color code your tableaus, and actually if you're using Excel and you're going to go through and solve these step by step, it's kind of cumbersome to deal with different colors all the time, unless you're like really super savvy with Excel and know all the tricks and things like that. So the colors aren't necessary, but they're just to illustrate what the different parts of the Tableau are. So let's just, for this video, let's just go through and see how we've translated the problem. So we had two original variables, x and y. So x and y are two columns of our Tableau. We added three new variables, s1, s2, and s3. So we have in total 5 variables in our problem. So this blue region here is just identifying the labels of our variables, and the information about those labels is stored below in the rest of the Tableau. The numbers in yellow are just the numbers that we see on the left side of our 3 equations. If we go back up and look at our problem, we see x plus 2y plus s1 equals 150. Well, that's what this first row is saying. It's saying x, 1x here, plus 2y plus 1 times s1, and then plus 0 s2 and 0 s3 gives us our 150. The second equation is the same. 3x plus 4y plus s2 is equal to 200. So we just translated the numbers, 3, 4, 0, 1, and 0 for the corresponding variables, and that when we sum all that up, we're going to get 200. And we do the same for the third. 5x plus y plus s3 is equal to 175. So you see 5 times x plus 1 times y plus a 1 times s3 is equal to the 175. Now the only other thing we need to decide on is how to keep track of our objective function and its value for a given decision. So this is a stylistic thing. So our objective function is to maximize 10x plus 11y. What we end up doing is we start our first Tableau off. We put negative values for those coefficients. So we put a negative 10 here and a negative 11 here. And the reason for this is what it does is it will keep track of the value of z in this lower right-hand corner, which I've made red. If we put in 10 and 11, it would be the negative of that value, which would still be 0 in this case. So this is just a stylistic thing. But the way we run through this algorithm, you'll want to do it this way because it actually helps you follow how to make your next step and how to do your next step. Seeing negative numbers are kind of cues for telling you what to do. So this last row is just about our objective function. And it's keeping track of the value. So what's actually happening is, because we've assumed all our inequalities are of the less than or equal to type, and all of our numbers in our constraints are positive, and all our variables are non-negative, we're going to have a similar shape every time for a 2-variable problem, for example. It's going to be some kind of polygon, and one of the vertices is going to be the point x equals 0, y equals 0. So that's a feasible solution, even though it's obviously not optimal because it gives us 0 profit, but it is a feasible solution. So basically we're starting there always, and it's a search algorithm. We're going to search through all the different vertices until we find the best one. Because when such a problem does have a optimal solution, it will occur at a vertex. We've seen many problems where that's not necessarily the case. For problems that don't have solutions, but when a solution does exist, there's always some corner point of the region, the feasible set, where the optimal solution is obtained. There may be more than one, but we just want to find one. So what we're really doing with this Tableau is we're saying, let's assume x and y are 0, because that's feasible. And how I can see that in the Tableau is by looking at these numbers in the bottom row here in kind of this peach color. The variables that have non-zero numbers are actually the variables we're considering to be 0 right now. And the variables whose columns look like a 1 and all zeros, like S1, S2, and S3, those are the variables we're considering to be of a non-zero value, potentially. All right? So we keep track of those. Since the 1 in the S1 column is in the first row here of this yellow region, I just denote that over here in the left by an S1 under the variables. So these green variables, S1, S2, and S3, that's just keeping track of which variables we are considering are non-zero or have some value. So if we decide to make no products, what that means is S1 must be equal to 150, meaning we haven't used any of resource 1. S2 has to be 200, which means we haven't used any of resource 2. And S3 is equal to the 175 on the other side, which means we haven't used any of the resource 3. Again, if you think of these three, this yellow portion and the green portion to the right, as equations, we plug in 0 for x and y, then x and y contribute nothing. So this first row is just saying S1 plus 0 S2 plus 0 S3 is equal to 150. Second row is telling us that 0 S1 plus 1 S2 plus 0 S3 is 200. And the last one is telling us 0 S1 plus 0 S2 plus S3 is equal to 175. So whenever we have a Tableau like this and we've kept track of the variables appropriately, it's telling us which variables we're considering equal to 0, which variables we're not considering equal to 0, and their values. And it's also telling us in the lower right-hand corner what is the value of our objective function for that specific decision. So what we'll do next is go through and actually see how do we manipulate one Tableau into a new Tableau that's still equivalent. It's giving us the same problem but looks different, so that we can see a new decision which is better than this one.